Hello? Hello? Can you hear me? Let's check the sound works, because that's normally the first thing I get wrong on this. Awesome, you can hear me. Okay, cool. I'm going to leave the chat open, and then if any questions and stuff come up during this, just give me a shout, and yeah, I'm going to explain what on earth this is all about, and talk a bit about assembly, and talk about Python, show you some tools, and then do some debugging and stuff like that. So yeah, the idea was actually a bit of backstory. So I started off reading a book on Black Hat Python, which is awesome. Started reading this one. In this book, I kind of got stuck on the chapters that were about creating shellcode. So the idea was that you use like buffer overflows to inject shellcode into remote hosts, and you can exploit it that way. And I didn't really know much about assembly, so I thought I'll read some books on assembly. So then I got another book, which was the Shellcoder's Handbook. And in the Shellcoder's Handbook, this one, which is also a good book, in the Shellcoder's Handbook, I kind of got stuck because it's been written for, first of all, it's been written for Linux, and secondly, it's kind of written for 32-bit operating systems, and all the examples like just didn't work for me at all. And I got pretty confused, and I think it was down to my lack of knowledge of assembly. So I got another book, which going further down the rabbit hole on beginning x64 assembly programming, which is a good book. And this one's by Joe Van Hoey. Maybe I'm pronouncing that wrong. But yeah, this one is also specific. He talks about Linux, but I've kind of hacked the examples to work with Mac. And as I was going through, I was kind of working with the samples and stuff like that, and I just thought, I wonder if I can get these samples to work from Python, and like what that would mean and how it would work. Yeah, there aren't many resources about x64 assembly. It's annoying actually, because like it's not like 64-bit is a new thing. It's been around for like what, 20 years or something, and it's a standard. You can't even buy. I don't even think you can buy 32-bit CBUs anymore. So yeah, it's a good book anyway. And I was kind of working through it and looking at registers and stuff, and it teaches you how to make command line apps. And I made a couple of simple ones for like counting numbers and doing loops and stuff like that. And I just wondered if I could plug that into CPython. So I wanted to show you a couple of things today. So kind of how CPython extension modules work. And I thought we could dig into a bit of those. If you're watching this and you've got little to no experience with assembly, that's fine. I'll explain some of the basic syntax and the instructions and what's happening as we go. So just a bit about my dev environment, I guess. This is Sea Lion. I'm on a Mac. It's a 64-bit Mac. You can't buy 32-bit Macs anymore. And there's a couple of tools I wanted to share with you. Sea Lion's debugger is really powerful. Hopper Disassembler is a great tool if you want to look at binaries and understand them. And then another tool called Signalizer, which is good for exploring binary files, not necessarily encoded ones. Hey Jay, welcome to the session. So yeah, let's start off, I guess, by I'm going to show you what this crazy thing does and why, and then we'll do some like live debugging and stuff like that. Hey Stefan. Okay, so I'm going to do the basics first. I'm going to. Okay, so I'm just going to get it running, and then we'll just do some debugging and have a look at what's going on. I think that's the best thing to do. So the actual extension, if we just forced it to recompile. So the extension is a shared library. The way that C extensions work in CPython is that you use setup.py. Actually, I did have one I was looking at yesterday. Let me just start that in the background. I'll come back to it in a second. So the way that you do this normally in in Python is that you have setup.py and you run a setup script and you build extensions. And in a package called distutils, or setup tools is an extension for distutils, there is basically like a Python wrapper for the C assemblers, for C compilers. And what it does is it will compile C code into a shared library. It includes the Python headers and it links to the Python library so that you can basically, it's like a shared object file, like a shared library. I'm just going to open a C example that I was looking at. This material does this weird thing. My machine's pretty good, but I think if you run CLine and PyCharm and Wirestream all at the same time, it kind of slows down a little bit. So let's give it a break. Okay. All right, so this is an example of a C extension for Python. If you've never written one before, you need to at least know C, but it's not too bad actually. Like it's fairly sensible, like how they've structured it and stuff like that. Come on. Okay, so this was like an example function that you could write in C that you could call from Python. So like if you compile this module, you can import it from Python and you can run this code. And the standard signature is that everything in Python is a Py object, whereas the objects are pointers to a Py object. A Py object is a basic data structure that has the type and the size of the two fields, but I can show you that in a minute. And then the second argument it will have is a pointer to an argument object. And you normally use this function called pyarg parse tuple, which will basically parse the arguments into native C types. So this thing here means parse the arguments into two longs, and then it's got variable arguments after that. So you basically give it a pointer to the first long and a pointer to the second long. There's a whole bunch of things you can do with this. If I share. What was it again? Pyarg, that's it. There's actually like a special syntax for this function that so this is it. So S is a string, S star is like a buffer, and then the ones I normally use are U for Unicode, which is a wide character, and then you can do, I was looking at longs and stuff like that. So this is a long. You could do a unsigned long, for example, like K, or you could do a short, for example, like a H. So like if I wanted to have a third argument in my function, which was a short, then I could just add a H and then just do the address of the third value. And it basically like unpacks the arguments into those addresses. So what will happen is when you run that function, pyarg parse tuple will look at the string and go, okay, the first one is L, so I'm going to cast that into a long. It doesn't actually cast it as another function that unpacks it into a native long object. And then it'll do the second one, which is a long, and then the third one, which is a short. If this returns null, it's because it failed to parse the arguments, and I'll show you what that looks like in a minute. And then you should always return a Py object from a C extension module. The easiest one to do is like a none, which is the reference is PyNone, I think it is. I might not have the object linked in here, but you can return just none directly. Or there's a whole bunch of utility functions to create Python numbers, strings, dictionaries from native C types. This one in particular, pylong from long, I'll show you in a minute like how that works, because Pylong is a bit weird. It's like Python, just pop this open, but like a number in Python can be like that long, and it doesn't matter, because under the covers that's actually an array of digits. So unlike C, where a long is a binary structure and it has a maximum value, in Python it's not like that at all. It's actually an array of digits, which is why you can have these ridiculously long numbers which wouldn't fit in a normal 64-bit address space. So what they've got is some utility functions to cast a long value into a Python long. The trouble is that if you try and cast that into a long, you're going to get overflows. So there's a whole bunch of separate methods for handling those situations. Anyway, so what does this have to do with assembly? It's important to understand this stuff if you want to go to the next stage. So what I wanted to see was, okay, so when I compile this, like what assembly code does it actually create? And I've got, here's the shared object file here, and here's just the native object. So I can load that in Hopper. Where am I? Okay, so there's two different types of outputs from this. The first stage is an object file, which is this one, which is the compiled code, and then the second stage is the shared object, which includes is basically after it's gone through the linking stage. So you'll get both. I don't really care about the linked version, because I'm only interested in the compiled version at this point. So if I jump into Hopper, if you've never used Hopper before, it's basically just a disassembler, but it's a really, really good one. It does pretty much anything you can think of. You can look at functions. Assembly does have like forms of functions, and they export symbols. So, for example, I defined a function in C called pyinit pycheck. If we jump back into PyCharm, you'll see it down the bottom. Where is it? Pyinit pycheck, that one. Yeah, that function there. So that basically turned into a function in assembly when it gets compiled. So the C compiler will convert that into a function. This one's quite simple actually. This is a good example. The first two this is pretty small. Let me see if I can make it bigger. Oh man. No? Okay. Surely I can like font. Why can't I make the font bigger? Does that do anything? No. Does that do anything? No. Okay, well sorry, it's probably pretty hard to read, but we'll see. So this is the compiled version. These are the instructions. If you're not that familiar with assembly, then there's like a few basic functions that you need to, instructions, sorry, not functions, that you need to know. Push, which pushes something onto the value stack. Pop, which pops it off the value stack. Move, which basically moves the right hand to the left hand. And load effective address, which basically loads the address of whatever's on the right hand into the left hand. You don't, with assembly, you can't like, if you're in Python, you just wanted to say a equals 1. That is simple. That's a simple statement. You can't do that in assembly because you can't copy from an address to you can't copy from like a variable to a variable. You have to first load it into a CPU register. So everything Are you on your phone? Yeah, this is going to be hard to read on your phone. You can't, so you kind of have to do it in 2 steps. So a lot of assembly code is basically just like, okay, copy this thing into a register, then copy it from the register into a second thing. So you kind of have to do everything in 2 jumps. So in this one, this is a really simple address, and what this does is these first 2 instructions are something typically called a prologue, which is just, you just always put these instructions in. It basically like preserves the stack pointer, and then before you return back, you always then take it back off again. So it's basically pushing RBP onto the value stack and then popping it back off before it returns, and then preserving the stack pointer so that when this function finishes executing, that the stack hasn't been corrupted. It really helps with debugging, and if you don't do this, then it can cause all sorts of crazy stuff to happen. Then you'll see load effective address of the module definition, which will, where did I go? The module definition keyword means that this is a 64-bit address. So it's saying load the address of the module definition into RDI, which is one of the CPU registers. Move OX3F5 to ESI. ESI is one of the CPU registers, but it's the 32-bit version. That value there might just look really weird, but that is 1033. Hopper probably does a conversion for you, but it'll make sense in a minute. I'll show you in a minute. And then do a jump to PyModule create2, which is part of the C API. So this function in assembly is basically just saying get the pointer to module def and load it into RDI. Copy the value of this into ESI, and then call this function, which is somewhere else. And when this gets linked, it all ends up being pretty straightforward. So what I did as the next step was to then okay, so why RDI and why ESI? I think if you're looking at assembly for the first time, they do not save the base pointers. I think if it's in debug mode, they would, but I think it depends on whether you compile it in debug mode. So why RDI and why ESI? So there's basically there's a convention with assembly in terms of like if you're calling a function, then which registers are used for which arguments. I've got it in the book somewhere, but basically what it ends up being is this is the first argument, this is the second argument, and that's the function. So what this is actually saying is run PyModule create with a pointer to module def as the first argument and OX3F5 as the second argument. If you go back and look at the code, where is it? I think it's a different version. Where is it? That one. Oh, that's confusing. I think it's because it's actually it's simplified it a bit when it's compiled it. Basically, what that's doing is saying that's module def, and that's the address of module def, and it's basically doing create to 1033. Like that's what that series of instructions in assembly is equivalent to in C. So I thought, well, okay, so if you can write this in C, then and it just creates a series of very simple assembly instructions, why can't you just skip out the C part and write this directly in assembly? And I was also learning assembly, so I thought this would be good and like a good exercise to do. So this is this is my assembly code. This isn't super easy to read either. Sorry, I'm just making everyone's lives harder. Let's go with 20. It might be easier. That didn't do anything. Okay, that's easier to read. Okay, so here's my assembly code. I'm going to skip the bit at the beginning and then go straight to the end. Okay, so this is the instructions that I created first of all, just to see if I could get this thing to register. This is, so in assembly you have 3 sections. You have data, BSS, which is, I can't remember what it stands for, but it's like not the actual hard-coded values, but effectively the variables, so addresses that you want to reserve. And then you have the text section, which is the actual instructions. So what I did first was basically copy these instructions. So I thought, if that's what C compiles it to, it makes sense that that is what it did. And I don't need a jump, because this is actually, all it's doing is just doing an extern. So I didn't need a jump statement. All I could do, what I could do instead is just do a call, and just call PyModule create2. And that is the 1033 that I mentioned, and that's the module definition. So I thought, if those are my instructions, block started by symbol, thanks Stefan. So if that's that, then that's pretty straightforward. So let's see if that, let me show you that actually working. I have here, let me stop it. I have here a source version of CPython, which I use for different things. And I'm just going to tell it to use the build folder. Right. Then I think what I can do is then run this. So this is CPython. I'm just compiling it from source in CLine, and then I have set the running folder to be the build output from my module. So I've compiled this already, and if I do import pymult, I don't know. Why isn't that working? It's because I'm running on 3.9. Let's try this one instead. I made a lot of changes to this yesterday, so no, it's annoying. Just trying to think how to do this. Could just cheat and just rename this. Hooray! Okay, there we are. That worked. All right, so it has tried to import my my module. What? That has nothing to do with my code. That's some I upgraded to 3.9.0 release candidate 1 yesterday, and I reckon I've got some old symbols left over from the previous version. Come on, wakey wakey. Okay. Apparently, why am I no longer streaming? Come on. Okay, I think I upset the Wirecast got upset because I decided to recompile CPython whilst streaming at 1080p, so I should be back. Let's hopefully that worked. Come on. All right, well, whilst that's recompiling, I'm going to jump back into the project and just keep an eye on the CPU because it's getting hammered at the moment. Okay, so what is module def? This one's really important. So when you write the code in C, then you give it you basically define a struct, and you just give it a name, which is module def, and the type is PyModule def. If you've worked with C structs before, basically they are just they're basically an instruction to kind of to the compiler, I guess. It's like a map of the actual memory layout. So it's not like Python where you have an object and you have fields, and like the fields could get initialized like pretty much anywhere in memory. These are contiguous, so if you have a struct, the memory will get allocated contiguously, and these will basically get allocated in sequence. So what this is saying is that there's a pointer to a piece of memory space which has this structure. And each of these is basically like a type, and types have a fixed size. So that it knows when it reads from memory, it knows like if it just gets a loads of zeros and ones, it knows what that means. So I can show you an example if it has finished recompiling. I think it has. Yeah, I think it's finished now. Okay, So, where are we? We have a breakpoint. Did it actually crash, or was it just moaning at me? Spec module. No, it didn't. It may actually have crashed. Let's see. No. Yeah, it did crash. Apparently, since upgrading Python yesterday, so I've just broken it completely. So that's not good. Let me just explain what's going on then instead. So with the structure, if I open, so it's called PyModule def, and it's in the module object header file. So this is a type definition. This is a struct, and when this gets compiled, basically it says this isn't it. If you see a pointer to an address, piece of memory, then load each of the parts of memory and put them into these fields, so that when you're referencing it, you can say the name, the docstring, the size, the methods, the slots. I can't remember what traverse is for. If you want a custom clear function, if you want a custom free function, and that's basically it. So what I did to construct this from assembly was to understand first of all the size of each of these fields. So if you generate the memory from assembly, you need to know exactly how big each field is. So first of all, mbase is module def base, which then contains fields. So what you have to do is basically like unpack that, and that then includes PyObject head. PyObject head is basically the first two fields of the PyObject, which is the size and the type. So that basically is two fields, size and type. And then this one is a pointer to a void. So this is a custom init function. So that's saying basically a pointer to the init function for the module. Index, I can't remember what index is for, but I just set it to null or 0 and it just seemed to work. And then copy, I can't remember what that does either. But yeah, this is basically as far as I got with this. So in order to call this function, so what I needed to do was first of all export a symbol, so a function, which is pyinit underscore the name of the module. That's easy enough. You can do that just by saying pyinit pymult, and then at the top you just make that a global. So when it compiles my assembly code, it converts this into a symbol in the library that it produces. So that's quite straightforward. Oops, that's quite straightforward. Then the next thing was to create this module definition. So this is a pointer to the module definition. It's not the actual address space. So in C, everything is by value. So if you want to send an address, you need to send a pointer, not the actual value. So module def is, okay, let me jump to the top. So what I then did is make NASM, which is the network assembler, does actually have a struct. It's like I think it's called a macro. It's like a shorthand basically, but it just allows you to say like allocate this block of memory. So what I did, I could call that Bob and it wouldn't matter. Like it doesn't matter what you call them, but I just gave them logical names. So this is the PyObject header. It is a reserve a queue, so a 64-bit address, and reserve 1. So it's saying reserve 64 bits. And then this is saying the type, so the object type, reserve 64 bits again. And then that init was a pointer, index was a pointer, copy was a pointer. So all of those will be 64-bit addresses. So allocate those. And then do name, doc, size, method, slots, traverse, clear, and free. All of those are pointers, so they were all 64-bit addresses. So I said, okay, to get the module def, hey, it's the other Anthony. Hey, welcome to the stream. So those are all 64-bit addresses. So module def then ends up basically being C button actually crashed. Let's see. $104 should be. The other Anthony. There's Anthony Satile just joined as well, who does a lot of streaming, and he's probably going to be judging me harshly on this. Okay, so that should be about 104 bytes. So the other issue I had was that, okay, it's fine, but you need to actually populate this with some values. So first of all, the module needs to have a name. So I just allocate dB means a byte data. ASCII is 7 bits, which you normally reserve 1 byte or 8 bits for ASCII characters. In assembly, you can just create strings this way by putting them in quotes, and it will then basically create like a char star, if you're used to C, like a char pointer, and 0 just means null terminate the string. If you don't do that, it won't know that the string is finished, and it will just keep reading into memory, which causes hilarious consequences. So that's my module definition. And then what I had to do was, actually create some memory with that structure. So this is the istruct macro. And with the istruct macro, basically what you do is you say, allocate some memory, some actual memory, using this structure that I defined at the top of the assembly code, and give it this name. I could have called that anything. It doesn't matter. I don't want to pick on Bob again, but I could have called it Bob. What's my favorite 3.9 feature? I'll get to that in a second. Okay, so then what you do with this is you say, at that offset, allocate this value. So at size, allocate DQ, data, like a 64-bit value of the integer number 1. At the type, allocate null, because this doesn't actually, module defs aren't actually an object, so you can allocate null as the type. It doesn't matter if I put 0x0 or 0. Like, I just for my own sanity, if I was referring specifically to null, continuation. Talking about features. Init function, I left blank. Copy index, left blank. The name of the module I put as the address of the string that I created earlier, and the name of the value for the pointer to the doc string I put as the value that I created before at the top of the function. The size I just allocated for 2. Seemed like a good number to start with. And then the methods I'll come to in a second. So when I initially started out, I just did this as null. So I said there's no methods in this function. In this module. Let's see if this works without exploding. So I'm going to spin up. I did actually have one. I had one that I prepared earlier. So if you do, okay, so pymult, if you want the doc string, you do dunder doc on the, and jazz hands, it gets the, it has properly allocated the string from the function. So it has effectively loaded the memory address that I allocated. Okay, so that was like stage 1, which was like how do you just even register the module? And all I basically did was recreate the memory, recreate the right sequence of bytes that represents a PyModule def, and send a pointer to that and call PyModule create to. Like that was the easy bit, I guess. Then I thought, well, that's not particularly exciting. and like having a module that doesn't have any functions doesn't really achieve a great deal. So what I wanted to do next was then actually have some methods. So the way that methods work in extension modules is they are a PyMethodDef. PyMethodDef, again, is a struct, has a pointer to a string, so the name, the PyC function, which is the actual method, effectively is just a reference to the function that's been loaded. Some flags, which are super important, basically say like what arguments does this method expect. They're meth flags, and there's a list of them in this file somewhere. Here they are. You can say variable arguments, keyword arguments, no arguments, object. This is a class method, or this is a static method. So you can basically say, like, this is my function and this is what it expects. And then lastly, you've got the doc string. So same process is to basically then create the method definition structure. So again, I did the name, the method, the flags, the doc string, and then I haven't really understood why yet, but when you write this in C, you do the method definition, you do the functions, and then you always terminate it with two null values. So and that seems to be like a null terminator for the module definitions, because you never provide a length. So because you don't provide a length, I think the way that it loads it is basically if it sees two null values in sequence, then it assumes that's the end of the methods. So, okay, so then this is basically name, method, flags, doc term. I just Terminator and Terminator 2, which was a much better movie, is basically the next step. So declare my structure, and then then actually create a method definition. So the name, multiply, the doc string, multiply two values. The flags I did as var args, and then all the other stuff. Actually, doc string I've made it null now, but whatever. And the terminators, yeah, and then the terminators just assign it here. So yeah, and then basically set the method field to the method definitions. So bringing all this together, basically it will create the memory sequence, including the method definitions, and it will set the symbol, the address of the function that it exports as the pointer to the method that it says that CPython should then call. Okay, so if you do the pymult, it does have this multiply, like it knows the functions there. It does all of this when it runs when it imports, like it reads the sequence when it imports. If CPython wasn't broken, then I could show you this in like live, but I don't know why it suddenly decided it doesn't have thread state. Like it wasn't doing that yesterday, and all I did yesterday was update to release candidate 1. Make disk clean, that is a good idea. Yeah, that's going to melt my stream again, but I'm going to give it a go. I am going to... Jeez, I need more RAM. Where is it? CPython C-line testing. No. I have too many copies of CPython. Did I put it? Okay, it's in my PyCharm folder. That makes no sense. there is also clobber, which is going to delete my configuration. I'm going to try disk clean first and see if that works. And I'm going to give it two cores. No. No, this is going to cause all sorts of problems. Okay. Whilst that's running, I'm going to go back to my assembly code. Okay, so this is fairly straightforward to this point. So we've got basically all we've done is just create a whole bunch of null values in memory. I don't think this is a particular accomplishment other than just being really fun to explore. But yeah, and you also have to link. So this is an external. Basically, it says that link it later. Like compile it first, and the linker can worry about how the hell it's going to reference this thing to an actual library. Okay, so let's get to the good part. So then I wanted to make an actual function that does stuff. My stream's breaking. I said 2 cores. Oh no, configure doesn't care, does it? It just does what it likes. Okay, so I wanted to make a function called multiply. So it's going to do some basic stuff. It's kind of equivalent to the C code that I was showing earlier. If I took that away and that away and that away and then that away and then said like long sts equals fal times fal2, like that's kind of what this is equivalent to. So yeah, the idea is then basically just multiply the 2 values. So what I did with this one, my machine is just having a really nice time here. Let's recompile CPython again, just to really push it over the edge. Okay, so this is my function. Here are my instructions. Number 1, preserve the stack pointer. Number 2, move the stack offset position, which is important. If something goes wrong in the process, then you can take that value back off again. If you want to read more about that, look up the calling conventions for just basically the calling conventions for the operating system. It tells you like why, and it has like a set of rules about like what you need to do with the stack pointer. So my goal was to run pyarg parse tuple to convert the arguments to the function to 2 longs. So what I did was create effectively 2 longs, x and y. A long is an 8-byte address, so 64 bits. So basically allocate some memory, 64 bits, x and y, 8 bytes. And then also allocate some memory for the result. So again, that will be reserve, and q is the quad word, which is the 64-bit address. And then the parse string is what I talked about earlier, which is in documentation, which is long. So convert the arguments into 2 long values. So my intention is to call this function, and that function, like we saw in C, the first argument is the arguments that were passed to this function, which is stored in RSI. So just copy those to RDI. The second argument is the parse string. So just get the address of the parse string and load that into RSI, which is the second argument register. Clear EBX because I think it had some gunk left over from the call, and then load the pointers to X and Y in the the third and fourth arguments. Yes, the third and fourth arguments. That should be third and fourth. Fourth arg. Okay, so load the address. This basically means that make sure that is a quad word and load the address of that into that register. Then call pyarg parse tuple. What that would have then done is convert the arguments that it was called to and put the actual long values in X and Y at the addresses that I specified. Then to double check that like this part here, like if the result of that, if it couldn't properly parse the tuple, then return null. So what I did with that one is basically test the result, and if it gave back a bad result, then jump to the bad input. So this is basically a go-to statement. Test if they're equal. So if that got back null, then jump to here, and if it did, then reset the stack pointer, add back the value that we subtracted at the beginning, and then return back. So effectively, like return null, and that will give you your value error, I think. Okay. It has recompiled, so let's see if that works in a minute. So if I do pymult.multiply and give it not longs, I don't know, I'll give it a letter A and then give it a banana. I've had too many coffees, I can't type. It will give a type error saying an integer is required, got type str. So instead of this exploding in a pile of flames, it will jump to the bad input section and return back the type error, which is nice. So that's CPython does provide some protection around this, so I don't have to worry about X and Y suddenly being something ridiculous. Then I've got to do the actual calculation. So if that wasn't null, then it will just continue down to this instruction. So load the value of X, which is the square brackets, into the racks register, and then multiply racks by the by Y. So basically, this, like I said before, you have to do everything in 2 steps. And all that's saying is multiply X by Y. And imul is an instruction for doing that, and the result will be in the racks register. So then move the result which is in racks into the result, the value of result which I reserved earlier. So once you've done that, then move the result, which will be the actual number, into the EDI register, which is what pylong from long will expect as the first argument. So when you run pylong from long, which I'll show you. So like pylong from long is part of the C API, and it expects one argument, which is the long value. So I'm putting that into the register so that it will use that value and then run this code. Oh, my stream's having a bad time. Okay, so once you've done that, then return back. I didn't, when you run this function, it will put the result into racks, the racks register, but I just leave it there so that the return result of that will just be left so that when it gets returned back, it will use that result. Whew, okay, that is it. So, you know, if you break it down into small steps, it's not that bad. Like you have to do a bit of experimentation to get it working. Let's see if it wants to play ball now. No, it's doing it again. Why is it doing that? This is annoying. I'm going to so what I'm going to do instead, I'm going to no, that's not going to work either. Alright, I can't show you the disassembled version, but which is a shame. Okay, so last step was type def indirection. Sorry, this was actually more straightforward than I thought it would be. How easy were the headers to read? What the headers, because I've just finished writing a book on the C Python compiler, I don't know quite a bit about the headers and the memory structure, so it wasn't that bad. But I think if you wanted to go further than this, then it would be quite tricky. I did want to add another function to do something more complicated than just multiplying two numbers. But yeah, I mean, I don't think it was too bad. Like once you get your head around it, then if you've ever worked in network programming, or you've worked with drivers or anything like low level in C, then you kind of know that a struct is like how structs work. Like I've done that sort of stuff before where you can just write, if you've got, actually signalize it, that's what I wanted to show. To get a better understanding of like binary structures and how they work and stuff like that, not hacking the government websites, but where was it? PyCheck. Let's open some binary files. Shared objects. Okay, so this is signalize it. I don't have any grammar applied. I think this is a Mac. Yeah, looks like it is. Okay, this is a nice tool if you ever want to like look into stuff. Basically, like it, you can give it these grammars. You can explain like the memory structure of a file format, and then you can open files, and it will follow that to basically like represent it in a GUI for you. If you ever like, I was playing with some Python bytecode. Let's open. I need a PYC file. Let's see if I can find something useful. I might have one. Yeah. Okay, this is a good example. This is signalize it, it's called. If you're interested in this sort of thing, it's really useful. There is a grammar for Python bytecode. I had to make some customizations to it because it didn't support the change in the bytecode moving to words. Long story. Anyway, So basically what this says is like, read this. This is all the binary data, and the grammar says that this file is formed of these chunks, and this is what they're called. So you can basically like look at it in a GUI. This is super useful, this thing, for reverse engineering stuff, or just like looking at all sorts of stuff. So you can look at this and say, oh, that's an instruction, that is the like that's the type, that's the extra, that's the flags. So you can actually look at this to basically disassemble Python bytecode. I know you can do that in Python anyway, but it's a useful tool. So yeah, if you do want to look at like how to recreate binary structures in assembly or in any other low-level language, this is a good place to start. C-line also has which is annoying because I can't show you because CPython is just not working today. Tell you what I'm going to do. I'm just not going to import it. I'm just going to run it and then pause. So it's going to be paused in a weird place. But what C-line will do is when you pause execution of the executable, it will know what variables are in the current frame, and then it will like represent them for you. So it kind of, I think it guesses what they are. So it knows that the prompt, which is, like these little signals, the prompt is a character string. So what you can do in C is you can just do like stupid stuff like this. Actually, no, that needs to be in quotes. I think. Well, it's probably just not going to let me do that. Oh, maybe it did. And if we resume, didn't seem to have any effect. Anyway, so what you can do is you can also right-click and do Show in Memory View, and it will show you the in hex. It will show you that variable in memory. So when you're debugging this stuff, it's super useful to be able to do this. So when you've created the binary structure and the program crashes, you can add a breakpoint before it crashed, get the address of the thing that you just created, and do Show in Memory View, and it will highlight the section of memory that it thinks it is, and then you can look at the bytes to actually see whether that is what you intended on making. For example, my PyMult, there's a nice little bug, which is the docstring for the function is not in the right memory address. So if I do, and the way to get the docstring for the function is to do help. Oh no. Oh, apparently I fixed that. Okay. That used to just cause a seg fault, but I think I maybe fixed it yesterday. So yeah, this is basically the idea and the concept. What I actually want to do with this is later in the assembly book, it has got a whole bunch of instructions, AVX and AVX2, which are like sort of more math intensive instructions for newer Intel CPUs, including matrix multiplication, because I'm curious to see, like, if I wrote a matrix multiplication or matrix transpose function in assembly, how much faster that would be than one written in C if it used the instruction sets that the CPU has. And Intel actually did this already. They wrote a I can't remember what it's called, high performance Python, and it was a version of the Anaconda distribution, and they targeted NumPy, because NumPy's got its own matrix multiplication, like the dot function in NumPy, if you've used NumPy, and it has a transpose as well. If you're not in this space, you might be wondering who the hell needs to transpose matrices. They're used very heavily in like machine learning algorithms and data processing. So machine learning especially, like most of the algorithms revolve around matrices, like transposing, multiplication, addition, subtraction of matrices, and those structures are quite hard for most languages to process effectively and quickly. C doesn't have a native equivalent to that, so the only way that you would kind of do it in C would be to write inline assembly in the C function, which is kind of gross, or you'd have to like write custom instructions. But Intel did the test and they reckoned it sped up NumPy by like 50% or something crazy for those types of tests. So finally wrapping all of this up, because I've been waffling on for an hour, okay, so it's in assembly. So what I wanted to do next is actually get this thing in a format that people can use. So normally when you publish a C extension, you write a setup.py and you use the build ext command. So if I'm in here, if you do build, it would like compile the extension. However, Distutils assumes, for good reason, that this extension is written in C because it is a C API. So it basically has a Python wrapper around the C compiler, and you give it like the source files for your you give it your sources, and it will like run GCC against the sources, build an object file, and then run the linker and link that with the Python library, and then create a shared library as the output. So when you run build in setup.py, Distutils will basically create a shared library from the source code by running either GCC or the Microsoft C++ compiler. So the stumbling block I came up against was I needed to run NASM because that's the compiler that I need for my assembly. So what I had to do was basically change my setup.py. You can basically say like I want my own custom commands to override the default commands. So what I did first was create a custom build command, and the interface will basically have a run function which executes. This code here doesn't really matter. I basically just copied and pasted it from the base class because you couldn't override the behavior of the base class. Distutil doesn't allow you to set your own custom compiler, but the command does actually have a property called compiler, and it expects that to be a C compiler, which is an abstract base class. And that implements a bunch of functions such as compile and link shared library, link shared object, link executable. So when you run build, it will basically like call these functions. The reason is because in Distutils they've got the C compiler, they've got the MSVC, like the Visual Studio one for Windows, they've got the Unix one which runs GCC, they've got the Borland C compiler. I don't know if anyone uses that anymore. So basically what they've done is they've added a layer of abstraction between the OS specific compilers and the build command itself. So I had a look at NumPy because I know NumPy supports Fortran. So I thought, oh, well, maybe NumPy figured this out. So what I did is made my own compiler class to override the Unix C compiler, because that's pretty close to what I wanted. And then just overrode some properties of it, such as instead of using GCC, it uses NASM. It still uses the CC linker, and then it still uses the AR archiver. So that's what creates the shared library off the back of it. And then after a bit of hacking around, I just set it so that it would add the right flags to NASM depending on the operating system. So it would use the Mac OS 64 object format for Darwin, which is Mac OS, and it also Mac OS. The symbols in Mac OS are always prefixed with an underscore. So this is just a little hack you can do. It's not really a hack; it's a solution you can do to make it work in Mac properly. And then if it's Linux, then it uses the ELF format and 64-bit because it's 2020. If the debug was parsed, then Anthony's got a. Of course, you've already done this, Anthony. Why don't I just ask you before? This is the kind of ridiculously edge thing that you would have already done. The other thing I had to do was like override the link function because I was having issues with it. It wasn't loading up the library directory and stuff like that. Anyway, so this I bundled with the package, and now when you run setup.py build like I did before, it will run NASM with the flags that I specified to create an object file. A distutils decides where that goes, and then it runs the linker, and the linker will link to the Python version that I am running from, and it will create the shared object. So why do you need distutils? If you have a source package and it includes C extension modules, you have to do this so that if someone downloads the source distribution, when you do pip install, it will actually compile it as part of the pip install. Because probably a lot of the scientific and math Python extensions that have C extension modules in them, they do this quite heavily, which is pretty much why Anaconda, like the Conda distribution exists, because a lot of them require special headers, or they require like weird compilers, or I mean like Fortran seems mainstream compared to some of the stuff in the scientific Python world. So yeah, this like running, installing a source distribution and having it compile as part of the pip install, like you have to basically implement this this API, I guess it is, to get that to work. So what I then did is include my little custom compiler in the manifest, include my source file in the manifest, and then when I do Python setup.py source distribution, then it will create the tar.gz file. And then if I did the binary distribution with a wheel, it would basically copy the shared library that it built into a wheel file, which is like an archive basically. So that when I do a pip, when I upload it to pip using Twine, then I don't mean pip, I mean PyPI. Let me show you. So if I go to pypi.org and then search for PyMalt, that's the one I prepared earlier. And you go to download files, it's got the wheel, which was built on my machine, and it's got the source distribution. The source distribution includes the assembly file, and if you downloaded that and run setup.py on it, then it would actually compile the assembly and link it on your machine. So wrapping this all up, what I then thought is, okay, how do I know that this works on not just my machine? So I wanted to add GitHub Actions for it. So I added a GitHub Workflow, a really simple one, one for Linux and one for Mac. I knew that Mac worked, so I thought, okay, let's start there. Try Python 3.7 and 3.8. Install NASM, and then run pip install pip and pytest, and then run setup.py install. If you run setup.py install, it will install from the source, including the compilation. And then finally, run pytest. So I wrote a very, very simple test for my code, which just said load the multiply two values, multiply 2 by 4, and check that it equals 8. So like import the library once it's done. So if you actually go and look at the action, and then look at build Mac, and then go to install dependencies, it does the pip install, and then here it's actually running NASM and compiling it, creating a shared library, copying that to the egg, and then deploying the egg into the packages and installing the egg. And then when I run test, it imports my newly compiled module and runs the test, and it passes. I had some issues with Linux, like it doesn't actually compile, but I need to work out why. So yeah, I mean, it works in GitHub CI now for Mac. So like if you, I think I demoed this yesterday, but like if you pip installed it, Python-y, install. I think those are the right flags. Yeah, then it should download and install that. That looked very quick, I think, verbose. This is what happens if you do a pip install. It actually downloaded it, and it downloaded the source distribution, compiled the source distribution, created the objects, linked the object, deployed the egg, and then installed the egg. So end to end, that is how you create an assembly module that can be used in CPython, distribute it via PyPI, and have anybody install it, as long as they're using 64-bit macOS. Like I just haven't had time to figure out why it doesn't work on Linux. It just seems to be some basic flags that I'm missing or something on the build. So yeah, that's it. That's the whole thing. Does anyone have any questions before I stop the stream? No? Okay, cool. All right, thanks everybody. Thanks for joining. Yeah, it's been fun to talk through this, and yeah, feel free to have a go anyway. And just download it and just check it out. And now that you can do setup.py, it's a lot easier than having like make files and stuff. Oh, my favorite feature for 3.9. The new parser, probably. The peg parser, which is now finished. Like it just makes things a lot more straightforward to understand. It just simplifies the parsing process. Like as a general user, it doesn't really make any difference, but the old one really needed a lot of work. Yeah, my only fear is that they end up adding all sorts of weird syntax just because it will now be supported. But yeah, the new parser is pretty neat. And yeah, there's just a whole bunch of things they fixed in 3.9 as well, which is nice. All right, thanks everybody. Have a great day, and thanks for joining.